It was never supposed to fail like that. When the boiler first reached full pressure, the readings looked stable, perfect even. Steam gauges steady, valves holding, fire roaring in a controlled rhythm beneath layers of steel and rivets designed to contain exactly this kind of force. Then, without warning, the metal changed its mind, not visibly at first, not in a way the operators could immediately interpret. A subtle shift in tone inside the chamber, a vibration traveling through the frame like a warning no instrument had been designed to translate into urgency. And then the rupture came, not as a leak, not as a crack, but as a violent, instantaneous release of stored pressure that turned water into expanding destruction faster than any human reaction could follow. In less than a second, the system ceased to be a machine and became an event, one that tore through brick, iron, and air as if all three were equally fragile. These boilers were never small. They were engineered to power entire industrial districts, factories, rail yards, textile mills, and early electrical grids that demanded continuous, high-pressure steam on a scale previously unimaginable. Each unit held enough internal energy to move thousands of tons of mechanical load through pistons, turbines, and interconnected systems. But power at that scale came with a condition that engineers understood, even as they pushed forward anyway. The higher the pressure, the smaller the margin between control and catastrophe. And still they built them larger, stronger, hotter, until boilers were no longer just components of industry, but central pressure cores of entire cities, hidden underground, inside factories, beneath streets where civilians walked unaware of what was held below their feet. When they failed, they did not simply break, they erased. Buildings collapsed inward, street grids fractured. Entire industrial blocks could be rendered unrecognizable in moments, as if the infrastructure itself had been folded back into raw force. And the question that followed these events was never about what happened. It was about why engineers kept building machines that powerful, knowing exactly what they were capable of becoming when control finally gave way. Before boilers reached the scale capable of powering entire cities, industrial civilization was already running into a problem it could not solve with smaller engines. Demand was growing faster than reliable energy production. Early steam systems were simple, localized, and fragile. A single factory might run on a modest boiler connected to a handful of pistons or mechanical shafts. These systems worked, but only within narrow limits. They required constant attention, frequent maintenance, and careful control of heat and water levels. A slight imbalance in pressure could stall production. A fuel shortage could shut down an entire facility. Industry, however, was no longer operating within small limits. By the early 19th century, factories were no longer isolated workshops. They were becoming interconnected production networks. Textile mills demanded continuous motion for spinning frames and weaving looms. Ironworks required sustained heat for smelting and forging. Rail systems emerging across Europe and North America required locomotives that depended on powerful, consistent steam generation. And beneath all of this, cities were beginning to rely on centralized systems of production and power rather than localized craft and manual labor. The older methods could not keep pace. Water wheels, once the backbone of early industrial power, were geographically limited. They depended on rivers, seasonal flow, and stable terrain. Wind systems were inconsistent and unpredictable. Animal labor was insufficient for large-scale mechanical operations. Even early steam engines, while revolutionary, were constrained by size and output. Factories began to outgrow their own energy systems. A single production line could consume more power than an entire early boiler could reliably supply. As industrial output expanded, engineers attempted to compensate by installing multiple small boilers across different parts of facilities. But this created inefficiency. Heat loss increased. Coordination between systems became difficult. Maintenance demands multiplied. There was no centralized control of energy, and without centralization, industrial growth began to fracture under its own weight. The problem was not simply production, it was concentration. Factories needed more steam, delivered more consistently, at higher pressure and across wider mechanical networks. But the existing systems were designed for containment, not expansion. Each unit operated independently, creating a patchwork of unstable energy sources rather than a unified supply. At the same time, industrial cities were expanding outward at unprecedented speed. Urban populations surged as rural labor moved toward factory work. Housing, transport, and infrastructure all began to depend indirectly on steam-powered systems. Railways connected cities into economic corridors that required synchronized industrial output across entire regions. The demand was no longer local. It was systemic. Industry needed a way to generate massive continuous energy output from a single source capable of feeding multiple systems simultaneously. Something stronger than individual boilers, something that could be scaled up without collapsing under its own internal pressure. But early engineers understood the central contradiction immediately. Steam power at larger scales was not simply a matter of increasing size. Pressure increased exponentially with volume and heat. The larger the system became, the more destructive its failure would be. Containment was no longer just an engineering problem. It was a matter of structural survival. Early boiler explosions had already revealed this danger in smaller systems. Even modest industrial units, when poorly maintained or overpressurized, could rupture violently enough to destroy workshops and kill workers instantly. These incidents were often treated as isolated accidents, attributed to operator error or material weakness rather than systemic design limits. But the pattern was becoming harder to ignore. As pressure increased, so did instability. As demand increased, so did pressure. Still, industrial expansion continued, because the alternative was stagnation. Rail networks could not slow down to match energy limitations. Textile production could not reduce output without losing market dominance. Steel manufacturing could not revert to older methods without collapsing under global competition. Entire economies were now structured around continuous industrial acceleration. So engineers pursued a solution that seemed both logical and dangerous at the same time. Build boilers that could handle extreme pressure at unprecedented scale and centralize energy production into fewer, more powerful units. Instead of many small systems, create fewer large ones. Instead of distributed energy, create concentrated force. The goal was efficiency, but the consequence was escalation. Early attempts at scaling boiler systems revealed new challenges almost immediately. Heat distribution became uneven across larger chambers. Metal fatigue appeared faster under sustained high pressure. Rivet joints and welded seams experienced stress points that could fail without warning. Even small imperfections in construction became critical vulnerabilities when amplified by scale. Maintenance also became more complex. A larger boiler system meant more surface area under pressure, more internal volume to regulate, and more potential points of failure that required constant inspection. Operators could no longer rely on simple observation or basic gauges alone. More advanced instrumentation was introduced, but early measurement tools were still limited in precision and reliability. Despite these challenges, pressure to expand did not decrease. Industrial leaders saw opportunity in scale. If a single boiler could be made powerful enough, it could replace entire networks of smaller systems. It could stabilize production, reduce labor costs, and increase output efficiency dramatically. In economic terms, the risk was justified by potential dominance. This logic pushed engineers toward increasingly ambitious designs. Boilers grew larger, operating pressures increased, fuel combustion systems intensified, safety margins narrowed, and gradually what had once been a simple industrial component began evolving into something far more dangerous: a centralized pressure system capable of holding enough energy to destabilize entire industrial zones if failure occurred. The machine that would eventually become known for its catastrophic potential was not born from recklessness alone. It was born from necessity layered over competition, ambition layered over limitation, and a growing belief that industrial power could be scaled indefinitely if engineered carefully enough. But the system they were building had already crossed a threshold. Beyond that point, every improvement in power came with a proportional increase in what failure would cost. The rise of the ultra-power boiler did not begin with a single invention, but with a gradual escalation in industrial ambition that pushed ordinary steam engineering beyond its original limits. In early industrial Britain, boiler design was still conservative by necessity. Engineers worked within known material strengths, cast iron shells, riveted seams, and relatively low operating pressures that could be maintained with predictable safety margins. These systems powered early textile mills, small foundries, and localized mechanical workshops. But as the 19th century advanced, industrial competition transformed boiler design from a supporting technology into a strategic asset. Factories were no longer isolated producers. They were nodes in expanding economic systems that competed across cities, regions, and eventually continents. Whoever could produce more steel, more textiles, more locomotives, and more manufactured goods gained control over markets that were rapidly becoming global. Energy became the deciding factor, and steam became its dominant form. Engineering firms began to experiment with scaling boiler output far beyond traditional limits. In industrial centers such as Manchester, Birmingham, and later in American hubs like Pittsburgh and Chicago, manufacturers collaborated with engineers to push pressure ratings higher in pursuit of efficiency and output density. One of the key developments was centralization. Instead of multiple small boilers scattered throughout a factory, industrial planners began designing systems where a single large boiler plant could supply steam through pipe networks to multiple production lines. This approach reduced maintenance redundancy and improved fuel efficiency, but it also concentrated risk into one structural point. If the central boiler failed, the entire system failed. That trade-off was accepted because the benefits were immediate and measurable. Higher pressure systems produced faster mechanical motion. Faster motion meant higher output from industrial machines such as looms, presses, and rolling mills. In industries like steel production, higher steam pressure enabled more powerful forging and shaping equipment, allowing manufacturers to work larger volumes of metal with greater speed and precision. By the late 19th century, boiler engineering had become a specialized field. Companies such as Babcock and Wilcox in the United States and various British engineering firms began producing standardized high-pressure boiler systems designed for industrial-scale deployment. These systems featured improved water circulation, reinforced steel construction, and more sophisticated safety valves intended to regulate extreme internal conditions. Governments and industrial regulators began to take notice only after repeated failures. Boiler explosions were not rare events. They were recurring industrial disasters. Entire factory sections could be destroyed when pressure containment failed. Investigations often revealed a combination of factors: material fatigue, poor maintenance, operator error, and sometimes flawed design assumptions that underestimated long-term stress accumulation. Yet instead of slowing development, these failures often accelerated it. Each disaster created pressure for stronger construction standards, which in turn allowed engineers to justify even higher operating limits under the assumption that improved materials and better design would compensate for increased scale. This cycle of escalation defined the evolution of the giant boiler system. Industrial adoption spread rapidly because the economic incentives were overwhelming. Railroads required massive centralized workshops capable of maintaining locomotives and producing parts at scale. Shipyards needed continuous high-energy systems to shape iron hulls. Urban factories demanded uninterrupted power to support growing populations of workers and consumers. In large cities, boiler systems were no longer confined to factories alone. They became infrastructure. District heating systems began using centralized steam plants to warm entire neighborhoods. Early electrical generation systems relied on steam turbines driven by high-pressure boilers. Hospitals, administrative buildings, and commercial districts began integrating steam distribution networks into their foundational design. In this way, the boiler was no longer just a machine inside industry. It became a machine behind civilization. The most powerful systems were often housed underground or inside reinforced industrial complexes to contain their physical footprint and reduce surface-level hazards. These installations were massive, involving multi-story boiler rooms, fuel storage systems, water treatment facilities, and extensive pipe networks that extended outward like circulatory systems, feeding entire urban zones. The engineers designing these systems understood the stakes. They were not unaware of the risks. Technical literature of the time contains detailed discussions of pressure thresholds, material stress limits, and explosion dynamics. Safety valves, pressure gauges, and redundant release systems were developed precisely because failure modes were already known. But knowledge did not eliminate expansion. Because industrial demand continued to grow faster than safety constraints could restrict it. By the early 20th century, boilers had reached a scale where a single unit could power multiple industrial districts simultaneously. These systems were treated with near reverence by operators, not only because of their importance, but because of the constant awareness that they held immense destructive potential if mismanaged. They were installed in reinforced structures, monitored continuously, maintained under strict operational protocols. And yet, even under careful supervision, failures still occurred, not because engineers lacked understanding, but because the physical limits of steam under extreme pressure created a condition where absolute control was never fully possible. Every advancement in capacity brought the system closer to its own threshold of instability, and the higher that threshold climbed, the more catastrophic the consequences became when it was crossed. By the time these boilers reached their most extreme forms, capable of powering entire cities, the distinction between industrial power and stored catastrophe had become almost impossible to separate. At its most fundamental level, the giant high-pressure boiler was a controlled transformation chamber. It converted heat into pressure, water into steam, and steam into mechanical force strong enough to drive entire industrial systems. But unlike smaller boilers, its scale did not simply multiply output. It amplified every internal condition, heat distribution, material stress, and pressure imbalance, until the machine behaved less like a component and more like a contained geological event. The structure began with the pressure vessel itself, a massive cylindrical shell constructed from thick steel plates, often riveted in early models and later welded as metallurgy improved. The walls were layered, reinforced at stress points where internal pressure would concentrate most intensely. These shells could span multiple meters in diameter and extend horizontally through entire industrial rooms or vertically through reinforced chambers. Inside this vessel, water was introduced under controlled conditions. It was not ordinary boiling. It was pressurized phase transition. As heat from the furnace system intensified beneath or around the chamber, water was driven beyond its normal boiling point while remaining in liquid form due to containment pressure. This created a state of stored thermal energy, waiting for controlled release. The furnace itself was a secondary core. Coal, coke, or industrial fuel was burned continuously in a firebox system engineered for sustained combustion. Temperatures inside this chamber could reach well over 1,000 to 1,500 degrees Celsius, depending on design and fuel efficiency. Airflow systems regulated oxygen intake through draft channels, ensuring combustion remained stable enough to avoid flame collapse, but intense enough to maintain pressure generation. Heat transferred through metal walls or internal tube systems into the water chamber. There were two dominant configurations. Fire tube systems, where hot gases passed through tubes surrounded by water, and water tube systems, where water circulated through tubes exposed directly to furnace heat. Each design carried different advantages. Fire tube systems were structurally simpler, while water tube systems allowed higher pressure operation and faster steam generation. As heat continued, water molecules began transitioning into steam at accelerated rates. This steam expanded dramatically in volume, creating internal pressure that accumulated within the sealed vessel. That pressure became the machine's driving force. At operational scale, internal pressure could reach hundreds of pounds per square inch in early industrial systems and significantly higher in later high-pressure designs. This force was not static. It fluctuated constantly as fuel input, water levels, and load demand shifted throughout operation. The steam did not remain contained. It was directed. A network of valves, regulators, and pressure release systems controlled its movement into mechanical infrastructure. The most critical component was the main steam valve system, which determined when and how energy would be released into connected engines or turbines. When opened, steam surged through iron and steel pipelines into piston chambers or turbine assemblies. In piston-driven systems, steam entered a cylinder and expanded rapidly, pushing a sealed piston forward with immense force. This linear motion was then converted into rotational movement through connecting rods and crankshafts, powering mechanical systems such as factory lines, pumps, or transportation engines. In turbine systems, steam was directed onto angled blades mounted on a rotor. The expanding gas flow caused continuous rotation at extremely high speeds, converting thermal energy into mechanical and eventually electrical output. Every stage of this process depended on precise balance. Fuel input determined heat intensity. Heat intensity determined steam generation rate. Steam generation determined pressure buildup. Pressure determined mechanical output, and mechanical output determined industrial productivity. But the system was never stable in a permanent sense. It was dynamic, constantly adjusting to changing demand. When factories required more power, fuel input increased, raising furnace temperature and accelerating steam production. When demand dropped, systems had to carefully reduce combustion without allowing pressure to fall too quickly, which could destabilize connected machinery. This balancing act required constant human oversight. Operators monitored pressure gauges that tracked internal conditions in real time. Early gauges were mechanical, relying on spring-loaded needles or mercury columns to indicate pressure levels. While effective within limits, they lacked precision under extreme fluctuations, forcing operators to interpret trends rather than exact values. Sound became another diagnostic tool. A steady boiler produced a deep, consistent rumble from combustion and steam flow. Changes in pitch, vibration, or rhythm could indicate rising pressure instability or mechanical strain inside the system. Experienced operators often detected danger, not through instruments, but through auditory shifts in the machine's behavior. Temperature was equally critical. Metal surfaces around the boiler could reach extreme heat levels, requiring insulation or protective barriers to prevent structural damage and worker injury. Uneven heat distribution created internal stress points within the vessel, increasing the risk of fatigue failure over time. Vibration traveled through the entire structure. As pressure increased, mechanical components began to resonate. Pipes shook subtly under load. Rivets and joints transmitted force across the frame. In high-output conditions, the entire system could enter a state of low-frequency structural vibration that signaled extreme internal energy levels. The smell of operation was unmistakable. Burning fuel produced dense combustion byproducts. Hot metal released metallic traces into the air. Steam leaks introduced bursts of superheated moisture that carried both heat and chemical residue. In enclosed boiler rooms, this created an atmosphere that was physically heavy, difficult to breathe, and impossible to fully escape. The machine's rhythm was continuous: combustion, pressure buildup, steam release, mechanical output, reset, repeat. But unlike simpler machines, this cycle never fully paused. Even during reduced output, internal pressure had to be maintained to prevent system collapse or inefficiency. This meant the boiler was always active in some form, always holding energy within its structure. And that is where its danger emerged. Because the same conditions that made it powerful contained heat, stored pressure, and continuous combustion, also made it inherently unstable when pushed beyond design limits. If the balance between heat, pressure, and containment failed, there was no gradual breakdown, only release. And at this scale, release meant destruction measured not in mechanical damage, but in the restructuring of entire physical environments. Inside the boiler house, time was measured by pressure, not hours. Shifts did not truly begin or end in a clean boundary. They overlapped with maintenance cycles, fuel demands, and the constant need to keep the system from drifting outside safe limits. The machine did not recognize rest, and neither did the work built around it. You learned this quickly if you worked near it, not through instruction but through exhaustion. The heat was not occasional, it was permanent. It pressed into your body even when you stood still, even when the boiler was running within limits. Clothing never fully dried, air never felt clean. Every surface carried warmth that did not belong to the human body. And the noise never stopped. A constant industrial roar, punctuated by sharper sounds, valve releases, pipe contractions, the metallic ringing of stress traveling through steel. Over time, workers stopped trying to separate sounds into meaning. They learned only one distinction: normal and not normal, safe and not safe. But even safe conditions were still dangerous. Coal-fed boilers produced ash and microscopic particles that filled the air. Early industrial ventilation was often inadequate, especially in enclosed boiler rooms built underground or within dense factory complexes. Workers breathed air that carried both combustion residue and metal dust from aging infrastructure. Long-term exposure was not considered in early design philosophy. It was accepted as part of labor. The most immediate danger, however, was mechanical failure under pressure. When a boiler reached critical stress, there was rarely time to react. Small warnings, rising gauge needles, irregular vibrations, unusual sound shifts could appear minutes or seconds before catastrophe. But interpreting those signals required experience, attention, and sometimes luck. If containment failed, it failed completely. A rupture transformed stored thermal energy into explosive expansion. Superheated steam moved faster than human perception, stripping structures apart in its path. Brick walls collapsed inward or outward depending on pressure direction. Steel components fragmented under sudden release of force. Entire rooms could be erased in moments, leaving behind twisted metal and scorched foundations. Workers in proximity rarely survived such events. Even those outside immediate blast zones could be injured by secondary effects: flying debris, collapsing structures, or scalding steam exposure. These incidents were recorded, investigated, and sometimes partially explained. Material fatigue, improper maintenance, overpressure events, design limitations. But beneath technical language was a simpler truth. The machine contained more energy than its environment could reliably restrain. And yet, despite repeated disasters, boilers only grew more important. because industrial civilization had already been built around them. Rail systems depended on steam-powered maintenance yards. Factories relied on centralized energy distribution. Cities expanded infrastructure around the assumption of continuous high-pressure output. Entire economic systems were structured on the reliability of machines that were, at their core, volatile pressure vessels. Regulation eventually followed catastrophe. After major industrial explosions in different regions, governments introduced inspection laws, certification systems, and engineering standards aimed at reducing risk. Boilers were required to undergo regular pressure testing. Safety valves became mandatory. Material standards improved as metallurgy advanced. These changes reduced frequency of catastrophic failure. But they did not eliminate it. They reduced probability, not possibility. Over time, however, a deeper transformation began to occur. New forms of energy and mechanical systems emerged that did not rely on centralized high-pressure steam in the same way. Electrical generation expanded, allowing energy to be distributed without maintaining massive pressurized cores inside urban centers. Internal combustion engines shifted mechanical power away from stationary boiler systems toward distributed mobility. Later technologies refined efficiency further, reducing dependence on large-scale steam infrastructure. Gradually, the giant boiler system lost its central position, not because it stopped working, but because alternatives reduced the need for it to carry entire industrial loads alone. Large boiler plants were phased out or repurposed. Some became parts of electrical generation facilities. Others were dismantled entirely. In older industrial cities, remnants remain: massive steel shells, abandoned boiler rooms, and underground chambers that once held immense pressure now reduced to silence and rust. But replacement did not erase consequence. The legacy of these systems persists in multiple layers. In engineering, they shaped modern safety standards. Pressure vessel design today still carries lessons learned from early catastrophic failures. In industrial regulation, they established the necessity of inspection systems and operational accountability. In urban infrastructure, they influenced how energy systems are distributed, monitored, and controlled. And in human history, they left something less visible but more enduring: a workforce shaped by proximity to risk. Men who spent years inside environments where a single mechanical failure could erase entire rooms learned a specific relationship to technology, one defined by constant awareness of invisible thresholds. Even after leaving the industry, many carried that awareness with them. The memory of pressure systems does not remain in statistics alone. It remains in the instinct to listen for irregular sound, to notice vibration in metal, to recognize when a system is holding more than it should. Today, the idea of a boiler powerful enough to threaten entire cities feels distant, almost abstract. Energy is distributed, regulated, and hidden behind layers of infrastructure that separate daily life from the systems that power it. But that separation is the final legacy of the machine. It taught industrial civilization a fundamental lesson: that power is safest when it is no longer seen in its rawest form, and that the most dangerous machines are not always those that fail often, but those that succeed long enough for people to forget what failure once looked like.